Hi.
Okay, are you ready?
Yeah, I'm ready. Yeah, I hope.
Um,
Yeah, there was some slight lag before. I hope it doesn't distract too much. Should be okay.
it seems fine.
Yeah. Okay.
Uh, okay, so hi everyone, and welcome to the first lecture of Giulio Tiozzo's mini course on Poisson boundaries for random walks on groups. Whenever you're ready, Julie.
Okay. Yeah. So thank you. Thanks for organizing this. This has been a very nice week at Infinity so far. So far, one day and a third has been at Infinity. So I'll bring you also at Infinity in some other ways. So basically, yeah, this is the plan of my talk. I also posted on my website some lecture notes about at least the first lecture, and then tomorrow I will update it with the um, newer part. So what's the plan? So the plan is, well, first of all, to give an introduction to Poisson boundaries, because as Ruth mentioned, there are many ways to talk about boundaries of a group in geometric group theory, and so there are more topological ways, and the Poisson boundary is one of the most important probabilistic ways. And of course, the interesting thing is there is a relation between topological boundaries and measure theoretic boundaries. So that's somehow one of the reasons why we care about it. And this is what we're gonna do at the end. So this will be somehow our final goal. So today we're going to start with talking about somehow some introduction to random walks, and in particular, the most important part would be the definition of the Poisson boundary, because one of the slightly annoying things about this field is that the actual definition of the Poisson boundary is one of the hardest things. Once you digested the definition, it's easy somehow. I mean, you can say things about it, but somehow the definition is one of the hardest things. And so I think even from also coming from a perspective, maybe some more group theoretic or topological perspective, it might be a little off-putting because it seems like there's lots of probability or dynamics or ergodic theory. So in fact, I will present it in a way that I think should be as familiar as possible to people saying geometric group theory. And then tomorrow we're gonna delve into more the technical part of the theory of Poisson boundary, which is very rich theory. And so in particular, our goal, the final goal, would be to identify the Poisson boundary, which is measure theoretic, to provide some identification criterion. So the identification criteria are built using this entropy theory. So tomorrow we will discuss all this machinery. And then in the last day, finally, we will sort of reap the benefits, and we will see what applications we can give to geometric group theory. So we will prove the identification of the Poisson boundary for certain groups that you guys probably care about, like hyperbolic groups, relatively hyperbolic groups, and the mapping class group. And in particular, what is the newest thing is the sublinearly Morse boundary, of course, that Kaspar is carefully introducing us to. And so, in fact, we will give one of the main application would be to, in fact, use to prove that this sublinearly Morse boundary indeed is also good, not just topologically, but it's also good from the point of view of measure theory, because it will indeed provide a model for the Poisson boundary. So that's somehow the setting. So, okay, so let's start with some brief introduction to random walks. There are many, I've given many introductions to random walks, and you can find them in many places. So I will just go slightly start to fasten this part, but still let's recall what a random walk is. Well, the most fundamental, the easiest example that everybody knows about is, you are on a line, and you can move to the right or to the left with probability 1/2. So this is the setting of classical probability, basically. So every time you pick plus 1 or -1 with probability 1/2. And so we write this by saying that the measure associated to this random walk is the delta mass at 1 plus the delta mass at -1 divided by 2, just to say that it's you take +1 with probability 1/2 and -1 with probability 1/2. And then what you do is you consider the sum of these increments, right? So each time xi is xi would be an increment of this random walk. So it could be either +1 or -1. And then these increments are IID. So they are identically distributed and they are independent. And so you take the sum of those and this gives you your walk. So that's the classical notion from probability. And you can think of this as doing a random walk on the Kelly graph of the group Z, which obviously is just a one-dimensional grid. And of course, we know things about this random walk. So we know that, for instance, this random walk is recurrent. So you almost surely you're gonna come back to 0 infinitely many times. So this random walk, so this random walk here is recurrent, meaning that the probability Wn equals 0 infinitely often is 1. So in this case, basically there is no going to infinity. So if we are after going to infinity, this is a pretty disappointing case because this random walk comes back to the origin infinitely often. So we don't want to really address this type of random walk. So of course, what you would want to do is you could do in higher dimensions, you can take a d-dimensional grid instead of taking one-dimensional grid. And then of course, we know that, for instance, if you do a random walk on a two-dimensional grid, well, it's still recurrent. But if we do it on the three-dimensional grid, well, the random walk becomes transient. So in fact, you don't return to 0 infinitely often. So this is a very famous result of Polya that says that for d equals 2, the random walk is recurrent. But for d at least 3, the random walk is transient. So of course, yeah, so transient means that probability that you random walk that we will do not always at Wn, and you will see in a minute why, the probability that Wn comes back to 0 infinitely often is in fact 0. It's kind of interesting to see that there is no the behavior is either you 0 infinitely often with probability 1, or you come back infinitely often with probability 0. Basically, there is no intermediate behavior. Well, because these are IID random variables, so if you come back once, you come back often, and so forth. So all these are interesting cases, but still, in this case, you do go to infinity. But so what does it mean that you're going to infinity here? Well, you do go to infinity, but you sort of go to infinity very slowly. So in fact, one thing you could do is you could measure the drift of your random walk. So you could say you can measure how fast you go to infinity, and you would go to infinity with speed 0 in this case. So it's still not so satisfactory from that point of view. So in general, we have the definition that we call the drift of the random walk. Well, it's just the speed, or speed of the random walk. is, yeah, it's just the limit as n goes to infinity of the distance between the end step of the run and walk and the origin by n. So, and well, it's not obvious, but it is true in most cases that this limit exists almost surely. So, and it's almost surely the same number. And so you see, there's another way you could think of going to infinity. So you could ask whether this drift would be positive or would be zero. And in fact, for this case, for a symmetric random walk, even in 3 dimensions and even in higher dimensions, it's still, the drift is still zero. So for symmetric random walk on V E, the drift is zero. So in some sense, you go to infinity, but it's still very slowly. So defining what the boundary for such a walk is, will turn out into discovering that the only boundary that you could have would be just a trivial boundary. So the only way to compactify this space in the sense of probability is just to add one point. And we will see all this very precisely. This is just some sort of set of examples to keep in mind. So the last example that we want to keep in mind is the random walk on the free group or on a tree. So what do we know about the random walk on the free group or on the tree? Well, this one is pretty different. So we consider the Cayley graph of say free group in 2 elements. So generated by A and B, and with the standard generating set. So the Cayley graph is this covalent tree. And so you can think of, you have A inverse, B and B inverse. And if you choose these elements with probability, with the same probability, so you do A or A inverse or B inverse with the same probability 1/4, then this will generate a random walk on this 4-valent tree. However, this random walk will be very different from the previous ones. So in fact, first of all, what it turns out is that this random walk will have positive drift. So in this case, so first thing is the drift is positive. And in fact, this could be an exercise you could do. So the way to prove this is, the idea of this is to consider the distance of the n-step random walk from the origin. So you consider dn, which is the distance between the n-step of the random walk and the origin. And you can prove expectation of this random variable grows linear. So in fact, you can prove that the expectation of dn is bigger than n/2. This is a good exercise that you can do. And as a consequence, if the limit in the definition of drift exists, then you could show that this indeed is positive. So this random walk is completely different from the previous ones, because indeed it has positive drift. Of course, you immediately, as a geometer, you would realize pretty immediately that there's a striking difference between the geometry in this case and the geometry in the grid case. So in the grid case, of course, this space is not hyperbolic in the sense of global, while in the free group case, this space is hyperbolic. And so somehow, the idea is indeed that whenever you have some element of a hyperbolicity, this would tend to make your drift beam. And moreover, in a suitable sense that we might discuss later on, it's also true that almost every sample path for this walk converges to the Gromov boundary of this group. So the Gromov boundary of this group is obviously a Cantor set. And so basically what happens is that almost surely your walk will choose a direction. So basically you start from here, your path, well, can backtrack, can do some crazy things, but basically, eventually, it would converge to some point on the boundary. So for instance, at some point, it will decide whether it stays in the upper part or in the lower part, or in the right part, or in the left part. So you see, if you divide your boundary in 4 parts, your walk will eventually choose one of the 4 parts and stay there forever. And so you say that it converges in the closure of that part. And then you can do this at every stage, and it turns out that this walk will indeed converge to the goal. So in this sense, you could.
Sorry, can I? So formally, for you, a random walk is just a measure on the group.
I will define random walk.
Okay.
Very soon.
Mm-hmm.
Yeah. So yeah, this is just to. Positive drift implies. Positive drift does. Does imply transient random walk, because almost surely you will be. Your distance from the origin would be bigger than some number cross n, and so you cannot be in a ball around it. Yeah. Are there any questions? Other questions? I will define everything in a second. This is just to give you some panorama of examples that you might have seen before. So that was just to connect with this. Okay, so now maybe it is indeed time to give a formal definition of random walk. So what is the formal definition of random walk? So the formal definition of random walk is the following. So you start with G countable group, and we start with the probability measure on G. So for instance, in the previous case, we consider some finitely supported measure. So we considered, in this case, we considered just a measure that goes either to +1 or -1. Or in this case, you consider the measure supported on A inverse, B, and B inverse. And so this tells you what is the increment of the. And then there are 2 spaces of two sets that we have to consider to define the walk. And so, so basically there's 2, there's the space of increments. So we pick a sequence of elements, Gn. We pick a sequence Gn of elements of G, and all these are identically distributed. So what this means? So it means that I start with taking another probability distribution, and we take another element G2, but it's independent element.
We've lost Giulio.
Oh, hello.
Oh, So
Yeah, sorry, there was some. Yeah, there was some. Yeah, there was some connection issue. Yeah, sorry about that. Yeah. Okay. So yeah, so the point is what I was gonna what I was saying here. So what is this? What is this definition of random walk? So basically, we take this measure on the group, and we take a sequence of elements, and the sequence of elements are independent and identically distributed with distribution. So we pick. So for instance, if mu is supported on two elements, so if mu is 1/2 delta A plus delta B, it means we pick either A or B with probability 1/2, and we write G1. And then we do it again independently of before, and we write G2, and so forth. So you see, so these GIs are called the increments of the walk. So GIs are called the increments, or GNs. And these are IID. But what we care about is not so much the increments, but we care about the product of these elements. So we call it Wn is the product. And so Wn, the elements of Wn, the sequence Wn, this is called the sample path. And clearly, very importantly, of course, these are not IIDs because you're taking this product, and so it's quite unpredictable what happens when you take this product. And so what we care about is to study this sequence Wn for a generic path. Okay. So yeah, let me get rid of this. Let me do it again from scratch. Okay, so in particular, and the other thing that we have usually, we have a group action. So we have G, a group of isometries of symmetric space X with symmetric B. And then we pick a base point in X. This would be a base point. And then we can also look at whatever happens when you take this random path and in the group and we act. We take it about, yes, exactly. Exactly. In the example that we had before, our GNs would be A or B's. So in the example, if mu is 1/2 delta A plus delta B, some path would be some product. So Wn would be some product, something like A, B, B, A, B, something like this. So each of them would be one increment. Of course, if you have also the inverses, this creates a bit of an interesting dynamics because you could have some simplification and so forth. Okay. Yeah, very good. Yeah, it's good if you have questions. It's good. Okay. So what we care about is action on a space sometimes. So if this is our space, so we take a base point O, and then we act by W1, so we get W1O, and then we get W2O, and then WNO, and so forth. And of course, the way I drew it, I'm thinking about maybe G being SL2R acting on the Poincare disk, which is of course one of the examples that we have in mind, and this space would have a boundary, which is the circle. So the question would be whether this random walk also converges in a suitable compactification of obvious space. So that's one question. So in particular, right, so that the last example to keep in mind is that if you take a G, some subgroup of SL2R, for instance, and then of course you can think of this, think of this as, or maybe PSL2R, you can think of this as the isometry group of the upper half plane or the Poincare disk. And so in this case, a measure would be you pick some set of matrices and you consider products of these matrices. So you can say, take mu to be, you know, one half delta A, delta B, means you take the matrix A with probability 1/2 and matrix B with probability 1/2, and your Wn would be A, B, something like this. And then you can act on a point and you consider this pair. And everything's clear with the definition, because this definition is of course very important. So more formally, in fact, we need two spaces. Two spaces of paths, in some sense, of sequences, which is very important not to get confused about. So one is the step space. So the step space is indeed, it's the space of increments. So this is the space of increments. And the space would be just, you take the product of G countably many times, and the measure mu, just the product measure. And so the elements of this will be denoted by this Gn. And this one are IID. But then what we care about even more is the path space. So what is the path space? Well, the path space is the space of the products, is the space of the W. So the path space, so basically you can consider a map from Gn mu n into another space, which is also, as a set, is also Gn, but we're gonna call it omega to distinguish it. And the map is just that you have a sequence Gn and you produce the sequence Wn, where each Wn is G1. So you see, the elements are also sequences of group elements, but the measure is different because this Wn's are not IIDs anymore. So if you push forward the probability on the left, you're gonna get the probability measure that we're gonna call P. So P is for us the push forward for this. So this is the somehow formal way to define space in which all these sample paths live. And also, there's also two shifts, which are very important to remember. So there is a shift on the space of increments. And the shift on the space of paths. And so two shifts do different things. So sigma will be the shift in the space of increment. So sigma of Gn is Gn plus 1. And there will be another shift map, which is from omega to omega, which would be in the space of paths. So these two different things are not conjugate to each other. They do two different things. So it's very important to remember this. Yeah. So sigma is nice because it's measure preserving, because it's just a shift in this space where the measure is the product. So t is different. So what does t do? T is just a time shift. So this just, you have a path. It's like a reparameterization of the path, right? So you have a path for your walk, W1, W2, W3, W4. It's like you're forgetting the first element or something. Yeah, it's like you're forgetting the first element, but it's just a time shift. Leaving the location of the walk fixed. So this is yeah, it may seem confusing, but it's important to make this pretty explicit, because sometimes we're going to consider one dynamics and sometimes the other, and they're pretty different. Okay, maybe this is a good time for questions, because the setup is very important, and maybe could be confusing sometimes. Okay, so yes, could you do an example of what the shift maps do? Yeah. Well, basically, I mean, so yeah, so basically, again, so, yeah. So more or less, I explained what t does. So what sigma does is a bit more annoying. So recall that n is g1, g2, gn, so forth, right? So yeah, so if we apply, right, so if we call this yeah, if you call omega this sequence of gn, well, if you do sigma of omega, you're forgetting the first one. You're getting g1. So the new path, when you apply sigma, the new path to wn prime would be something like is g2 gn. So it moves the path basically. So it's g1 inverse of wn. So in geometrically, it really moves the path. While tau doesn't move the path, just changes the time. So that's what I would like to say. Does it make sense, or you still have question? Okay. Okay, so now we got this over with this Tony issue. We can ask, okay, what are some questions that we can ask? So the questions that we can ask about boundaries of random walks are of various types. There's maybe four questions that we like to ask. So first of all, does the random walk converge almost surely to a suitable compactification or suitable boundary of X, right? So we have our space X here, and we start with the base point, and we have our path, and then we want to know whether there is some compactification of X in which this boundary, this random walk actually converges. And as I said, this in cases where there is some hyperbolicity of the space, it's pretty it's pretty common. And so, for instance, let me quote one famous example here. Famous example is if you have a random walk in PSL2R. There's a famous lemma by Furstenberg, who somehow is the originator of this theory, which says that if you have random walk on subgroup of SL2R, unless the walk, the measure that you choose is as a support, as a very special support, then this walk will converge to the boundary of the disk. So let me say like this. So if mu is a non-elementary measure, and I will tell you exactly what that is in a second, on PSL2R, then for almost every path, for almost every sample path, there exists the limit psi equals the limit as n goes to infinity of Wn of say point O is a point in the boundary of the disk and exists. So, but what does non-elementary means? Well, non-elementary means that it's not supported on a compact subgroup or does not fix a finite subset of the boundary. So basically, it means that the group generated by the support of mu is not contained, in this case, is just in a one parameter subgroup. Because in SL2R, well, you could be contained in a group of rotations around 0, and then, of course, you're not going to go to 0. Or you could be contained in a parabolic subgroup, and in that case, you can only converge to one point, which is the boundary of this, which is the parabolic fixed point, or you could be contained in a power of a loxodromic element, and so you would preserve a geodesic. So these are kind of the cases where the group generated by the support is still small, so you don't see the whole geometry of the disk. But Furstenberg says that as soon as the group generated by the support is somehow large enough, then this walk will choose some direction. Of course, the direction it chooses will depend on the sample path, particular sample path. But almost surely you will pick some direction. So this is one question, and it's a very important question. And in fact, whenever there's hyperbolic features for X, you would see that, in fact, this is what I proved with Joseph Mara, that basically, whenever your group acts on a hyperbolic space, then the random walk does indeed converge almost surely to the boundary, again, under some non-elementarity condition. But we will not focus so much about this question at this level. So what is the second order question is, well, how good is the convergence? So suppose we are in this good situation. So we have this nice convergence. So now the question is, can we actually compare this random path with the geodesic? So you see, you would have, say in the disk, you would have a path from the origin to this boundary point, but you can also just draw the geodesic. And so again, you kind of want to compare the geometry with the probability. So you want to ask, well, how good is this approximation? And so, in particular, one thing that people care about is the sublinear tracking property, and we will see that this property is absolutely essential when we want to discuss things like the sublinearly Morse boundary, of course, because this is defined in terms of sublinear properties. So, of course. So what is a sublinear tracking property? Sublinear tracking property means that the distance, so the sublinear tracking property means that yes, there exists gamma, a geodesic ray into the space such that the distance between the end step of your walk and gamma at times, well, L times n, because you have to rescale by the drift if the geodesic is parameterized by arc length, divided by n. That's this way. So you have Wn here, and you have a point on the geodesic, and you want to know that this distance is pretty small. Can you guys hear me? Yeah, okay, good. Yeah, actually, maybe this way is yeah, you see bigger. Okay. Yeah, so this is the this is the sublinear tracking. So and we will see later. So the sublinear tracking property is closely related to the Poisson boundary. So we need to establish the sublinear tracking property to identify. But I haven't told you what the Poisson boundary is. Another question that I really care about is what are the properties of the Hitten measure? So first of all, we need to define the Hitten measure. So, well, what is the Hitten measure? Well, the Hitten measure is the following. It's just the probability of hitting certain subset of the boundary. So if almost surely Wn of a point converges to boundary of X, then we can define the Hitten measure as mu, and so it's nu of a set is just the probability that the limit will converge to this set. So you see, you have your space, and you have a subset of the boundary. And so A, and you want to ask what is the probability that your walk will converge to that. So this Hitten measure, very importantly, depends on your starting measure mu. So in some sense, it would make sense to put the subscript mu here to remind you that it's not just a property of the group, but very much a property also of the measure that you put on. And in particular, one question you could ask is, well, if this boundary has many different measures, for instance, if you're in the case of the disk, well, the disk definitely carries the Levesque measure, for instance, and you could ask whether this Hitten measure is the same class as, or if it has the same dimension at least, and things like that. Or if you have a Patterson-Sullivan measure, you could ask whether the Hitten measure is in the same class as the Patterson-Sullivan measure, and things like that. So these are all nice questions. However, so this number 3, I will not touch too much, but what they really care about is, for this course, would be the Poisson property. So presentation formula that we will go over very soon, which is establishing a duality between the space of bounded harmonic functions on the group and the space of bounded measurable functions on the boundary. So this is one possible notion of telling what the boundary is. Well, the boundary space such that you realize this duality coming. And this duality is an analogy of the classical duality coming from PDEs or complex analysis between harmonic functions on some domain and the bounded measurable functions. And so the big question that we have in general is, and I will specify much better, but the bigger question is this: given a random walk on a group of isometries of some space with a notion of boundary, for instance, the Morse boundary or Gromov boundary or sublinearly Morse boundary. So you need two things, such that random walk converges almost surely to this boundary. So this is the first condition, which is geometric condition. Otherwise, it's strange to talk about a boundary in this random walk sense. The question is, do we have a Poisson representation formula on this boundary? And so if this is the case, we call this the Poisson boundary. So again, I will give the precise definition. It's a bit involved, but that is the core of the idea of what the Poisson boundary is. And again, you see immediately something that maybe sometimes you hear about in geometry, which is the Poisson boundary of a group. Well, to be really precise, you would have to talk about the Poisson boundary of the pair, the group with the measure. So in principle, it depends on the measure. What is still true, though, is that in most cases that we care about, in some sense, for every reasonable measure that you put on your group, well, if you look at the measure that you get on the boundary by this hidden measure, well, you will either basically, if you have a Poisson representation formula for one measure, you will have it for a very large class. So in some sense, you don't quite see it so much when you mention this result. Technically, this is absolutely crucial. This is an invariant of the pair of the boundary, the group with the measure. Okay, so now let's look at the Poisson-Fürstenberg boundary. So sometimes we just call it Poisson boundary, but this theory indeed comes from Fürstenberg, so it might make sense to call it Poisson-Fürstenberg boundary. So sometimes I will. So let's look at the original Poisson representation. So what does the original Poisson representation formula says? Well, it says the following. So we look at the space of harmonic functions. So what are harmonic functions in just complex analysis? Well, these are functions that are zeros of the Laplacian operator. And we want them bounded for some reason. You will be clear. So, and what is the classical theorem says? It says that there is a correspondence between harmonic functions on the disk and bounded functions, bounded measurable functions on the boundary of the disk. And so how does this correspondence work? Well, how do you go from a function on the disk to a function on the boundary? Well, the easiest way to do it is you just take a limiting value. So you go radially. So if you have a function inside, in a point on the boundary, you can go radially, and you hope that there is a limit. And by Fatou's theorem, there is almost surely a limit if the function is bounded. And so you can define your function on the boundary by taking the limit of the function inside. So that's one way. The other way would be a probabilistic interpretation, which is you could take a Brownian motion. It doesn't matter that you know the definition of Brownian motion, but if BT is a Brownian motion, well, you could say I start the Brownian motion from the center of the disk, and I look at the value of this function as I take this random path. And if I condition on converging on this boundary point, so I take all the paths that converge to this boundary point, and I average this function along this path of the Brownian motion, then I get the function on the boundary. And it turns out that these two definitions are equivalent because the Brownian motion is very symmetric on a disk, because of course the disk has lots of symmetries. The metric is rotational symmetric, so the headed measure, in fact, for the Brownian motion is just the Lebesgue measure. Now, on the other hand, how do we go back? How do we go back? So, well, the way we go back is doing what is usually called a convolution with the Poisson kernel. So this is the theorem that you might have seen in complex analysis or PDEs, and you always wondered what it meant. So, well, there is this classical theorem that says that if you consider the Poisson kernel, which is the following function, so you consider this Poisson kernel, and if you have a function on the outside, on the boundary, then you could construct a function on the inside. So you see, if you have a function f, so you want to construct the following. So you want to say that I define the function like this: u of r e to the I theta. If I'm inside the disk, it's 1 over 2 pi integral minus pi to pi of f of e to the it. So this is a function on the boundary. And then I take a convolution. So I take this Poisson kernel and I do this convolution. And what is somewhat magic is that then, yeah, so then u is harmonic. In the classical sense, this is just a classical theorem. So the Laplacian would be 0. And yeah, so this is the way you are taught in complex analysis. And I was always wondering what this means, because it seems pretty I don't know. It seems pretty mysterious to me why this formula in particular. But it turns out that there is a very nice interpretation, and which will bring us much closer to what we want to do for discrete groups, which is interpreting this Poisson kernel in terms of the action of SL to R on the boundary of the circle. So, are there any questions so far? Okay, so let's go through this correspondence in another way. So we have our disk. And so recall that basically you could think of the disk or the hyperbolic or the upper half plane as SL to R. So SL to R is the unit tangent bundle. So this is basically SL to R mod SO SO2. So it's just modulo the group of rotations, because the group of rotations fixes a point. So okay, so if we kind of blur slightly this distinction between SL to R and the disk, we can do the following. So if I fix point 0 and I fix some other point A inside the disk. So let's pick a point A, which is RE to the I theta. So this would be the coordinates. And then, so there exists a Möbius transformation, G in the isometry of the group, of the disk, such that brings 0 to A. Particular, which one is it? So it's G of Z equals A minus Z over 1 minus A by Z. So this is an exercise. This is the classical element that interchanges A and 0. But yeah, anyways, so what do you do? And now let's look at its derivative. So if we take its derivative and you take the modulus of its derivative, you can verify that this is 1 minus A squared, the norm of A squared divided by 1 minus A bar Z squared. And then if we interpret Z as a point on the disk, on the boundary of the disk, so Z is e to the IT, we get that G prime of e to the IT is 1 minus R squared divided by 1 minus R e to the I T minus T squared. Okay, so this one basically is the Poisson kernel if you can compare to what you had before. So you have this formula for the Poisson kernel, and this is written in exponential notation, but it's basically the same. So in particular, this means that you could rewrite your formula in the following way. So you would have you used to have that U of R e to the I T theta is the integral from minus pi to pi of f of e to t, the derivative of G at this boundary point, dt over 2 pi, so you bring the 2 pi in. So what is this thing? So this is, this is the derivative, the good old derivative of the action of G on the boundary. So if you think of it as acting on the circle with the Lebesgue measure, this is the Radon-Nikodym derivative of the Lebesgue measure for G. So this is the integral over the boundary of the disk of f of psi dg lambda over d lambda of psi d lambda of psi. So think about it. Why is this the case? Well, because this derivative is the Radon-Nikodym derivative. This is a formal map, so the derivative in the direction, I mean, the derivative is the same in every direction, and so in particular, it's also the derivative along the tangential direction. So it's the Radon-Nikodym derivative with respect to the Lebesgue measure. D lambda is just the normalized Lebesgue measure, so it's dt over 2 pi. And so we're taking this in. And in fact, well, I need one more. Sorry. Yeah, I need one more step. So we take, this is the same as the integral of xi dg lambda of psi. So you see that you can interpret the definition of this Poisson representation formula, this convolution of the Poisson kernel in a much simpler way. You look at the action of this group on the boundary. You start with the Lebesgue measure. You push it forward by G, and you integrate your F. So that's it. That's all there is. So this is this mystical formula. Indeed, just has to do with the action of SL2R on the boundary. I mean, this is not the secret, but somehow, for me, it was a revelation when I saw it. But of course, it's not the secret. It's just that sometimes it's hard to make this connection. So the point is that to write it this way, it's much easier to think about what you could do in a general group, because in the end, we don't have this Lie group. Of course, Furstenberg indeed start with these Lie groups, but let's say we have a mapping class group. So then you don't have this Lie group structure, but you still might want to, we still might want to do such duality. And in fact, that's precisely what you can do. So okay, so now we're gonna give the definition. So to do this, we start with studying the concept of more abstract concept of harmonic function. So now we have, say, a discrete group. It could be also locally compacted, but let's start with a discrete group for simplicity. So we have a notion of harmonic function on the group. So what's the notion of harmonic function? Well, it's a function that satisfies this main value property. If you start at G and you go one step, you go to GH, so you go to one step in one direction, and then you go in one step in every other direction, and you average, so this mu means that you're averaging over all possible increments, then you're gonna get back the original function. So you see, this is a discrete variation of the definition of harmonic function, not in terms of the Laplacian, because you don't have differential operators, but in terms of the mean value. And so then we have this space, which will be crucial for us, which we will call H infinity, which is the space of bounded harmonic functions. And dually to this, we have the notion of stationary measure, which is if you have a measure on a space, which this space, we think of it as being the boundary. So is a space on which G could act, say by homomorphisms, then we have a measure which is stationary if it's not invariant, but it's invariant on average. So you start with the measure nu, you push it forward by G, and then you're averaging. And if you go back to the same measure, then you call this measure. Now, an exercise you could do, which we might be able to do, is that an example of this is the Hitten measure. So if you have that the random walk converges almost, then the Hitten measure is indeed new stationary. So let's see, maybe. Yeah. So let's see, maybe we can try to prove this. So what do I want to show, right? So recall that the Hitten measure is the probability that the limit of n infinity of Wn is base point. So let's say nu of A. The probability that this limit belongs to A. And now we have various options. So the first element could be a whole bunch of them, right? So there are various possibilities for the first element of the walk, and so we want to somewhat disintegrate according to that. So let me write it down. So basically, what do we have? So we have the various options are that you have that the first element, G1, could be G, so you fix G, and then you have the probability that you're gonna hit A given that G1 equals G. And what is that? Well, so the first thing is clearly nu of G by definition. And now, what's the other one? Well, if you recall that Wn is G1 G2 to Gn. But if we condition on G1 equals G, so we know that this one is G. And so this one is, the probability is the same as saying that the limit of G2 Gn O belongs to G inverse of A. And now, since our process is stationary, the probability doesn't change if you shift the increment. So it turns out that this one is just nu of G inverse A. So you see that we proved the stationarity of the Hinton measure by definition. So now the question is, are there more than one Hinton measure? Are there more than one stationary measure? And well, this depends on the type of group that you look at. So for hyperbolic like groups, basically there should, but for higher rank it's more common. Okay, so
sorry, can I ask? Does the hitting measure not depend on the base point?
No, the Hinton measure does not depend on the base point in the situations that we have, because it turns out, it turns out the following. It turns out that the limit of, so if you do Wnx and Wny, it turns out that the distance between these two elements is the same as the distance between x and y. And so usually in the compactifications that we are interested in, or boundary that we're interested in, whenever two points have bounded distance and you go to infinity, they converge to the same. Yeah, so that's an interesting point, but yeah, somehow it is.
Okay.
Yeah. Okay, so in general, what are the ingredients that we need to have to define this Poisson boundary? Well, in general, we have a notion of mu boundary. So let's give this notion. So whenever you have a convergence to some space, you have mu boundary, and definition is this. So, and this is just a measurable definition. So a measure space nu, yes, on which G acts by homomorphisms. Is a mu boundary well, if there is a map G equivariant, everything is G equivariant map, a boundary map, so let's call it B and B, from the space of paths to your space B, such that now we go to this shift space. So V and D is equal to B and D composed with T. So it's independent. It's T invariant. So what does it mean? So T, remember, is this map that shifts the time of the path, but does not shift the location. So the most important example of this is precisely when you have convergence. So if the random walk converges to boundary of X, well, you can define the boundary of the point of a path. Well, this is precisely the limit of Wn of this point. So clearly, the thing is, what happens if you do boundary composed with T of omega? Well, this is the limit of Wn plus 1. But clearly it doesn't matter because it's just shifting the time. So this is also BND. So this is the first requirement for being a boundary. So the convergence implies that you have this boundary map, which is independent of this action. However, this is not enough for your map to be called the boundary, because you see every space can have a boundary. In this case, every group you just take a point. So one point compactification somehow like is a mu boundary. So right. So this is the remark. Is that yeah, for every group, you could take a 1 point with the delta mass is a new boundary. But what do we want really? What do we want? So we want a Poisson representation formula. So we want that there is a map from harmonic functions inside the group and L infinity functions on the boundary. And we want this map to be an isomorphism. Because you see, if you can always take the point compactification, and then, well, L infinity would be just constant. But maybe there's more harmonic functions. So if there are more harmonic functions, then somehow your boundary that you considered is too coarse. You want to take a boundary with more points so that you can produce more harmonic functions. And so that leads us to the definition of Poisson boundary. So basically, first of all, we need one more thing, which is the Poisson transform, which we already did basically, because we looked at this Poisson representation formula. So the Poisson transform is this map. We will call it P, maybe, from L infinity of B nu into H infinity of G nu. And it works like this. So you have P of a function. So we start with a function here. And this function, we want to compute it on a group element. Well, how do we do it? Well, we follow what we did before in this Poisson representation formula. We take the function f, we take the measure nu on the boundary, we push it forward by a group element, and when you integrate. That's a pretty simple formula, but this one works for every group. And it's, well, one can verify that the image of this function, this transform, indeed is harmonic. And that has to do with the fact that nu is stationary. And so from here, we finally can give the formal definition. Yeah. So we say that a mu boundary, which is a space with a stationary measure, a mu boundary, space with the stationary measure and a map from the space of sample paths into there is let's say a model for the Poisson boundary, or I'll explain why we usually say that. Well, if the Poisson transform is an isomorphism. So it's a map P from L infinity of B nu into H infinity G is an isomorphism in the sense that it's bijective. So if it's bijective, then it becomes an isometric isomorphism with these two Banach spaces. And so let me say a few remarks here. So, well, the first remark is that we say that the Poisson boundary is trivial. So we say that B nu is isomorphic to a point. So it's trivial. Well, this is equivalent to say every bounded harmonic function is constant. And this is sometimes called the Liouville property. Because of the connection with the other. So okay, so basically this is the definition. I will see that for certain groups, indeed, the Poisson boundary is trivial, so there are no other harmonic functions, and there's no nice way of quantifying the space except for just with a point, and that would be, for instance, for abelian groups or nilpotent groups. But for groups with hyperbolic properties, like the mapping class group or hyperbolic groups, indeed, this boundary is pretty rich, and then you want to ask whether, indeed, the model that you have in mind coming from this geometry is indeed satisfying this Poisson representation. Okay, so I think I'm done for today.